So in this lesson, we're going to talk about implicit differentiation. And in order to understand what implicit differentiation is, we're first going to discuss the difference between explicit and implicit. So if we have an explicit equation, that means we have it set up where we have our dependent variable, which is typically y, written in the form y equals, and then some expression in terms of x, or whatever the independent variable is. And by having it written like this, we can directly determine the value of y if we know x. So for example, if I have the equation y equals x squared plus 1. The equation has y on one side and everything else written in terms of x, or the independent variable, on the other side. And if I know the value of x, I can plug it in and directly find the value of y without having to rearrange the equation to solve for y. So that is explicit, and when we've taken the derivative so far with all of our equations, this is the kind of equation we've taken the derivative of. Now, the new method is if you have an implicit equation, and that's when you have some kind of equation where you have all terms of x and y mixed throughout the equation, and it's not solved for y. And you will not be able to directly find the value of y if you know the value of x. One well-known example of an implicit equation is the equation of a circle. So we have an implicit example here. So we have the equation of a circle, x squared plus y squared is equal to 25. So this is a circle with a radius of 5. And if you notice, this is not solved for y. All of my x's and y variables are all mixed in, and this is not solved for y. So if I wanted to write this in a way that was explicit, so that we can compare where it is solved for y, we would subtract x squared from both sides. So I would have y squared is equal to 25 minus x squared. And then I would have to take the square root of both sides, and I would have y equals plus or minus the square root of 25 minus x squared. So this is the example of how you would write it explicitly. When you have an implicit equation. A lot of times it's difficult to solve for y before you take the derivative. So that's why we have this strategy for taking the derivative called implicit differentiation. And so here is the steps that you want to take when the equation is set up implicitly. So the first step is you want to take the derivative of both sides of the equation, and you want to keep in mind that y is a function of x. It's not solved for y, but y is some kind of function of x. And so therefore, it's considered like an inner function. So when you take the derivative, you want to use the chain rule. The next step is you want to rewrite the equation so that all your terms that contain dy dx are on the left, and all the terms that do not contain dy dx are on the right. And that way, for step 3, you can factor out the dy dx, and then for the fourth step, you can solve for the derivative of y with respect to x by dividing both sides of what's left over when you factor. So here is our first example. This is an implicit equation because it's not solved for y, and all of our x's and y's are mixed up, and I can't solve for y directly if I plug in a value of x without having to do some additional algebraic manipulation. So we're going to use implicit differentiation here. So when I have x squared plus y squared is equal to 25, the first thing I want to do is take the derivative of both sides. That was step 1 of our problem solving. So when I do that, I want to take the derivative with respect to x of each term. Okay, now when I take the derivative with respect to x of x squared, I'm going to have 2x. When I take the derivative of y squared with respect to x, remember y is the dependent variable. So that y is some kind of inner function. So I want to make sure that I use the chain rule here. So I'm going to take the derivative of y, which is 2y, but then I'm going to take and multiply by the derivative of y with respect to x, whatever that is. When I take the derivative of 25, that's a constant, so I get 0. Our next step in our problem-solving strategy is I want to get all the terms that have dy dx in it on one side and everything else on the other. So since we only have one dy dx term here, I'm just going to subtract 2x from both sides. So everything that has a dy dx is on the left and everything else is on the right. Okay, so I subtracted 2x from both sides. Now the last step is to solve for dy dx by dividing by anything that's left over. So I'm going to divide both sides by 2y. So my derivative of y with respect to x is negative 2x over 2y, which I can simplify as negative x over y. Now it's pretty common when you're doing implicit differentiations to still have y's in your derivative. You just have to keep in mind what that y represents. Sometimes it's possible to first solve for y and then take the derivative the normal way that we've done so far. But if it's too complicated to try to solve for y, then this is the way to go. Okay, in the next example, we're going to use implicit differentiation with the product rule. So if you notice here, I have a product of two functions. I have x to the third and I have sine y. So when we take the derivative with respect to x of both sides, I'm going to take the derivative of x to the third sine y plus the derivative with respect to x of y, and then the derivative with respect to x of 4x, and then the derivative with respect to x of 3. All right, when I take the derivative of x to the third sine y, I got to remember to use the product rule. So I'm going to take the derivative of the first function, which is x to the third. When I take the derivative of that, I have 3x squared, and then I multiply that by sine y. Then I take the derivative of sine y, which is cosine y, times my function x to the third. But because I took the derivative of cosine y, I got to use the chain rule and remember to multiply by the dy dx. Then I'm going to add that to what I get when I take the derivative of y. The derivative of y is 1, but because I took the derivative of y, I have to multiply that by the dy dx. And I take the derivative of 4x, which is 4, and the derivative of 3 is 0. If you notice, these terms right here have a dy dx in them, so I want to keep those together on one side and everything else on the other. So I'm going to subtract the 3x squared sine y from both sides, so I'm left with cosine y times x to the third times dy dx plus 1 dy dx, I can just write it as dy dx, is equal to 4 minus 3x squared sine y. So now I have everything that has a dy dx on the left and anything that doesn't have a dy dx on the right. So now on the left hand side I can factor out the dy dx, and what's left over is the cosine y times x to the third plus 1 is equal to 4 minus 3x squared sine y. And now I can complete this by dividing both sides by cosine y times x to the third plus 1, so I can solve for dy dx. So my derivative of y with respect to x is equal to 4 minus 3x squared sine y all over cosine y times x to the third plus 1. And actually, it's probably even better and less confusing if we put the x to the third in front. So I would write it as x to the third times cosine y, and then plus 1. So this is my derivative of y with respect to x. In this example, we're going to take the derivative for a second time, and we're going to take the derivative, or the second derivative of x squared plus y squared is equal to 25. Now we've already, whoops, this should be written like this. That's a typo, since we're looking for the second derivative. We want to take the derivative of the derivative. So in our previous example, we found that the first derivative of this equation was negative x over y. So that was what we did previously. And now we're going to take the derivative again of both sides. When I take the derivative again of both sides, I'm going to get the second derivative, and then on the right I have to use the quotient rule. So I'm going to take the derivative of the top. The top is negative x, so I'm going to take the derivative of negative x, which is negative 1, multiply it by y, and then I'm going to subtract the derivative of the bottom, which is 1. So I take the derivative of y, which is 1, but because I took the derivative of y, I got to use a chain rule and write this as dy dx. And then times the top function. And this is all over the bottom squared. So this is all over y squared. Okay, now I know that dy dx is negative x over y. Right? We know this. So I'm going to substitute that in here and then simplify. So I have the second derivative is equal to negative 1y minus, and then I have a negative and a negative, the negative x and then the subtraction in the formula, so that's going to turn to a plus. And then I have x times that x over y, or the negative x over y, all over y squared. So this turned into a plus because of those two negatives. But when I did the substitution for dy dx, it's actually still negative because of that negative in front of the x over y. So just take your time and watch your signs. Now, when I simplify this, I'm going to get negative y squared minus x squared all over y to the third, because I would clear the complex fraction and then just clean up and add like terms. In the next example, we're going to find the equation of a tangent line to the curve x squared plus y squared is equal to 25. So again, we're dealing with a circle that has a radius of 5. The center is at 0, 0. So here's our picture, just a rough sketch. The center of the circle is at 0, 0, and the radius is 5. So this is the point 5, 0. This is the point 0, 5. This is the point negative 5, 0. And then this is the point 0, negative 5. So here's the picture of our equation x squared plus y squared is 25. We want to find the tangent line at the point 3, negative 4. So if we're looking at the point 3, negative 4, maybe we're looking somewhere around right here, just a rough sketch. So we're looking at the tangent line here. We already know from a previous example that the derivative, the first derivative, is negative x over y. So if I want to find the slope of the tangent line on the circle at the point 3, negative 4, I'm going to plug in 3 for x and negative y for 4. So I'm going to evaluate this at the point 3 and then y is negative 4. So when I plug in 3 and negative 4, I'm going to get that this is a positive 3/4. So this is my slope of the tangent line. So now I know what my slope is. I got to plug in my point x and y to find my b. So I'm going to plug in 3 for x, 4 for y, and I'm going to solve this for b. When I solve for b, I'm going to get that b is negative 25 over 4. So the equation of this line right here that just touches at the point 3, negative 4 is going to be y equals 3/4 x minus 25 over 4. In the next example, we're going to find a tangent line again, but we're going to use a different equation. So let's go ahead and find the derivative, so then we can plug in the point and find the slope. So I'm going to take the derivative of both sides. So I'm going to take the derivative of each term. Okay, when I take the derivative of y to the third, that's going to be 3y squared. But because I took the derivative of y, I have to multiply by the derivative of y with respect to x because of the chain rule. Then plus, I'm going to take the derivative of x to the third, which is 3x squared. Now I'm going to do minus. We have two functions here. We have 3x and then we have y. So I'm going to take the derivative of 3x, which is 3, times y, plus the derivative of y, which is 1, times dy dx, because of the chain rule, and then times the 3x. And then when I take the derivative of 0, it's just 0. So I now have to distribute this negative sign to the expression that we used for the product rule. So that gives me a minus 3y minus dy dx times 3x is equal to 0. Now, when I solve this for dy dx, remember, I'm getting anything that has a dy dx on one side. So this and this. Everything else is going to be moved to the other side by subtracting that term. And then I divide by what's left over when I factor out the dy dx. So when I solve this for dy dx, you should have 3y minus 3x squared over 3y squared minus 3x. So I'll let you try that step on your own. So see if you can get the dy dx. Now, this is the slope of the tangent line. And if we want to evaluate it at the point 3/2, comma 3/2, I'm going to plug in 3/2 for both x and y. So I'm going to evaluate the derivative at x is 3/2 and y is 3/2. When you do that, you're going to find that you get -1. So the slope of this tangent line is -1 at the point 3/2, 3/2. Now I got to find b, so I'm going to plug in 3/2 for y. I'm going to plug in -1 for my slope, 3/2 for x, and then I can solve for b. When I find b, you're going to get 3. So my final answer for my tangent line is going to be y is equal to -1x plus 3. So that's this line here, that's in orange. That's the tangent line at this point on the curve, 3/2, 3/2. Last example, we're going to do an application of implicit differentiation. And so the problem says, in a simple video game, a rocket travels around an elliptical orbit whose path is described by the equation 4x squared plus 25y squared is equal to 100. The rocket can fire missiles along tangent lines to its path. So the object of the game is to destroy incoming asteroids traveling along the positive x-axis towards the point 0, 0. If the rocket fires a missile when it is located at 3, and this should be not 85, this should be 3 8/5, where will it intersect the x-axis? So you have an ellipse, and it has a center of 0, 0. And this rocket is traveling around the path of the ellipse. And as the rocket travels and it fires its missiles, wherever that point is, that rocket is on the elliptical path, when it fires the missile, the missile travels on the tangent line. So when it fires the missile, if it's at this point and it fires the missile is going to travel this way. And so these asteroids are coming in this way, and the rocket is trying to shoot them down. So we need to find the equation of the tangent line at the point 3 8/5. So we're going to take the derivative of the ellipse, the equation of the ellipse. So I'm going to take the derivative of 4x squared, which is 8x, plus the derivative of 25y squared, and that would be 50y, but because I took the derivative of y, I gotta multiply by dy dx, which is the derivative with respect to x. And then when I take the derivative of 100, because x is a constant, I just get 0. When I solve this for dy dx, I'm gonna get negative 4x over 25y. So if I want to evaluate this at the point 3 8/5, that means I'm going to plug in 3 for x and 8/5 for y, and I'm going to get negative 3/10. So that's the slope of the tangent line. At the point 3 8/5. So, and then I got to plug in 3 8/5 so I can find my value of b. So I'm going to plug in 8/5 for y is equal to negative 3/10 times 3 plus b. And when I solve this for b, I'm going to get 5/2. So the equation of the tangent line is y equals negative 3/10 x plus 5/2. So if I want to determine where the line intersects the axis, I have to plug in y is 0, because on the x-axis the value of y is 0, and solve for x. So I'm going to put in 0 for y. And solve this for x. And I'm going to get, when I solve that for x, that x is 25 over 3. So this means the missile interacts with the x-axis at the point 25 over 3, 0. So at x equals 25 over 3, that's when the missile is going to hit that x-axis.